Welcome to our meetup today. This is part 3 of a series of 4 lectures on petascale architecture. The idea is not to throw up information and knowledge, it's just to do kind of a workshop and share with you kind of a basic methodology to get you start thinking on your first implementation of Petascale, to go over some challenges as we did in previous sessions, introduce several technologies maybe you're familiar with, maybe not, offer a way to compare them and to essentially make an intelligent choice about your choice of weapon, if you will, for your implementation. What I'm suggesting is merely a framework. It's not a consult. Nor will it be accurate in terms of cost analysis, of an ownership analysis, just a framework to get the discussion going. And I highly recommend you consult before you make an informed decision. But I hope you have fun. So in previous sessions, what we did is we went over some introductions and defined some jargon and some terms, so we'll talk in the same language. And then on the next session, we introduced the petascale use case of sensor data. Allow me to just bring it up. One second. Okay, I'm sharing my screen. If you want to engage from the chat, it's also okay, but you're more than welcome also to open your microphones. But if you're not speaking, please mute yourself so the recording would be crystal clear for everybody. From the chat, hi Paul, thank you for joining us. Okay, I'm sharing my screen. So before I go deep a little bit about myself, my name is Omid Vahdaty. I'm the founder of Jutomate, and I am the community organizer of Big Data Demystified. You're more than welcome to challenge and engage during this meetup, but take into account that I'm just human and I could make mistakes, but I just love what I do and I do what I love, and I'm happy to share and engage and discuss about anything that you're passionate about. About our community, Big Data Demystified, there's the community website, Big Data Demystified. Even the first part of this lecture is uploaded. You can press the link and get the history. If you need to catch up in terms of what was discussed, the slides are and the videos are there. In the future, we're hoping to add some executive summary so you'll be able to catch up quicker. And about me, I have over 20 years of experience in the startup industry and enterprise vertical as well. Third degree black belt in Taekwondo, skydiving habit. Nobody's perfect, and I like to lecture a lot about my passion, which is data. So we discussed, jumping on previous events, we discussed the terms and then we introduced the use case. Let me go over it again quickly. It's 1 petabyte sensor data where you have some analytical workload, 10 analysts that need to go over this data. The data doesn't go anymore. It's only one table with 5 columns: timestamp, geo ID, sensor ID, value, and sensor type. All the data is located on on-prem data center, but for the sake of the discussion, it doesn't really matter. We can go only about, we should go over only the database selection. All the data is compressed in a 1:5 comp ratio, 200 terabytes after compression. Then analytical users working a full-time job, query the data, assume 3 years worth of data, frequency of sensors every 10 seconds. For today's exercise, as I mentioned, we're going to go over database design. We're going to introduce this two databases, and we're going to go over them. Some people requested the link for the lecture. I'm putting in the past lectures in the chat, so you can review that. The use case is in the introduction level, which is here. But today's lecture haven't been published yet. It will be published for those who RSVP'd, yes. Someone asked for the YouTube channel. Yeah, sure. The YouTube channel is over here. Big Data Demystified. Over here. And I'm going to put it in the chat as well. You know what? I'll give you a better way to get there. On the Big Data Demystified website, on the home, you have YouTube link over here, and it should take you to the right place. Okay? Instead of memorizing the links, I'll help you get there, navigate there easily. Ooh, 500 subscribers. Good.
That's amazing.
Yes, lots of work by my teammates to make this happen. A lot of volunteering work to make this community a thriving community. Okay, let's start. Today's discussion is about BigQuery. And BigQuery, if we select BigQuery to implement this use case, there are several steps to go over them. There are the same steps for all the different technologies we are going to examine, so it will be relatively comparable with some minor adjustment per technologies. Usual opening, let's skip that, we did that. BigQuery. Okay, generally speaking about architecture and billing. It's not a course about BigQuery. I assume you know a little bit about BigQuery, but let's align a little bit. In terms of architecture, it's a scale-out architecture, which says a lot. We discussed about pros and cons of scale-out versus scale-up technologies. We discussed about auto-scaling. Since it's serverless, there's no auto-scaling. You cannot control anything. Let's add the word serverless here. Serverless. All you can do is do some reservation of resources and pay a fixed price instead of pay as you go. But if you choose to go pay as you go, you are going as tight as you can humanly can. And the price would be $6.25 per terabyte. It's a recent price increase, I think, from last July. Just a quick note about pay-as-you-go versus flat rate. Most people assume that if you pay as you go, you pay more than flat rate. It's not always the case. It really depends on your use case and your workload, and you should have some details, monitoring details about your use case. But generally speaking, I pulled more than once that pay-as-you-go could be about 30% cheaper than flat rate. So before you go on and commit to a vendor for 1 year for capacity, think twice. Or at least make an informed decision based on data and some workload and some experimentation around it. If you have some comments or questions, you're more than welcome to challenge me or ask.
Omid, this price is for BigQuery, right?
Yes, BigQuery. All this, the next 20 to 30 minutes would be around the BigQuery. I think 2 technologies today would be more than enough, assuming questions and discussion. So,
yeah, quick question about quick question about the pricing. You know, it's
sure.
$6.25 per terabyte. If I just use if the data is only 100 gig, so it's going to be divided by 10, right?
Yes.
Okay.
Yes. The minimum pricing though is per query is 10 megabytes.
10 megabytes. Okay, got it. Thank you.
Some people miss this, although it's 1 over 10,000 over dollar in terms of cost, but still, it's a fraction. If you run that by automation, it builds up to a number which is substantial. Although there are some tricks that only apply or valid when you abuse a pay-as-you-go system. Abuse, I mean, gain from the benefits of the fact that you're not paying for the backend, only for what you scan. It's a detailed discussion we can do later if you want. For now, let's focus on our use cases, but feel free to ask questions. So the minimum billing, as discussed, caching, another advantage that most people are not aware. They keep caching for 24 hours, which is a lot sometimes. Assuming your data freshness is daily, voila, why not utilize that? Colonel storage goes without saying. In petascale use case, you're gonna want colonel storage, and also it's applicable to our use case since we are talking about 1 table and 5 columns. It kind of makes sense. A nice thing about Google's philosophy is about the auto cost reduction, specifically on the cold storage of BigQuery, that after 90 days, the cold storage inside BigQuery automatically gets a discount. I don't remember the exact number, but it's around 50%, which is substantial. If you keep history of data and all you have to do is every now and then ask a question about the history. You should know that in terms of architecture, it's serverless and it supports both internal storage and external storage, and you can apply both and use them as you see fit. Both have an advantage and disadvantage, and we'll go over this, but you should know that both are acceptable. Let's fine-tune a little bit about the cost structure we discussed in the past, the difference between data scan and data read. In BigQuery, it's the same. So if you have 1 terabyte of uncompressed CSV and you are querying that, you'll pay $6.25 per terabyte. In other technologies where they support data scanned, which is takes into considerations the compression, the same terabyte will be compressed to 200 gigabytes on GCS. Therefore, you'll be paying, in theory, 20%, which is $1.05. But in BigQuery, you'll be paying the same amount. So the only thing you will be doing some cost reduction is the cost of the actual storage. You'll be paying 1/5 over here. Any questions about this?
Sorry, can you repeat? Why is it the same? If it's
Sure. Allow me to take the previous lecture just to be clear. In previous lecture,
when the data is compressed, of course you save a little bit of money on storage, but
yes.
you may have to pay a little bit penalty on the read performance. because it has to be decompressed.
Yes.
Yeah.
As we mentioned,
Okay.
yeah.
Okay.
Right.
So what you are saying, it's not
Yeah.
exactly one-to-one, but of course we have a benefit and we have a penalty. This is what you mean by saying it is the same. It's not necessarily the same, but I think it depends sometimes on the data profile, right?
Let's clarify that a little bit. I took the same slide from the introduction lecture, which is 2 lectures ago, when we examined the AWS Athena, which has the same architecture, which is serverless, and in theory the same billing structure, but only one minor difference. They bill you on the amount of disk space used after compression. This is the data scanned. So essentially, in Athena, you pay $1.
Okay.
On compressed, which is the same data. Uncompressed, you will be paying $5. Does this make sense?
Yeah, that makes sense. But let's go back to the Google example.
Okay.
Because that makes sense. But
so now in BigQuery, whether you are querying a compressed file of 200 gigabytes or uncompressed, which is the same data, just compressed or uncompressed, you will be paying the same amount because what they bill you is on the actual data in memory after compression.
Okay, clear.
Which is a major difference with some people.
It's a major difference. Okay, clear. Thank you for clarifying that.
Sure. Please feel free to ask questions. I'm here for the discussion, for the fun. Okay, so whatever you want, there's no stupid question, only things which are not clear enough.
You mean that the BigQuery will uncompress the data before a process?
Yes, every other agent.
But Athena didn't.
Both will do it. If you remember, both take the data, compressed or uncompressed, they ready to run, decompress if they have to, and they process and they show results. Same goes for the Athena. Same thing. Whether or not you decide to compress is entirely dependent on what we discussed.
Yeah, but naturally on GCP I will have a less motivation to compress.
No.
So explain.
So how about the performance query?
Because the price will be the same.
Many considerations around it. Let's start with the most basic one. When you save 1 petabyte instead of 1 terabyte, you pay about $20,000 monthly only on the storage.
Okay.
When it's compressed, it's 1/5, about $5,000, $4,000, give or take. 1 second, please. Sorry about that. I had to take that. So this is a major difference when you talk about petascale architecture and you need to do a TCO analysis, which is total cost of ownership, and the storage layer also has cost even if you're not querying it. So compression should be applied. I hope it was clear.
Yeah. Thank you.
So when you want to compare data scan and data read, as discussed, it will be the same in terms of billing. So why compress? As we mentioned, you should compress. But the question is, should you always compress? As a rule of thumb, yes. But what's the problem? The problem is when you have small files, the penalty of decompression time may be longer than the time it takes to process data. Does it make sense?
Yeah,
Yes,
and
no?
small file is like less than 100
Yes.
megabytes.
For example, even
Okay.
less.
No,
Case.
Yeah, lower. I'm saying lower than, okay. Lower than
Very
like
small.
1. So we need like, okay.
Okay. So, in theory, you should ask yourself another question. Wait a minute. So, in BigQuery, there are two options, internal storage and external storage. So, if I'm using external storage, naturally, I need to decide whether I compress or not, because I'm using GCS, right? Right. We just discussed it. But when I use BigQuery, I insert the data. So it's a serverless service. I know I have access to data. They save it in their own place and it's not accessible for you. So when should you use internal storage and when should you use GCS storage? So basically, if you are planning to query about 100 terabytes, it should work perfectly. But the more you grow, since you are bounded by resources, you're more likely to experience some pain. So you should have a combination of BigQuery hot data and some cold data and GCS. In theory, you can put everything in GCS and query it in BigQuery, but there will be some penalty in terms of execution because there are some optimizations when you insert data to BigQuery on the metadata and some data skipping. So there are some performance benefits.
So in BigQuery, looks like there's an option that you can use to say, I want to store this piece of data into internal storage and the rest of the into a object storage.
Yes.
Is that correct?
Yes. And the reason for that, because until 100 tera, you don't want to spend on over calculations. You just use BigQuery internal. When you go over 100 terabyte, you want to do some optimization, probably use some other technologies, probably do some your own type of optimizations of life cycle policy on the data, for example, deleting all files. So it kind of makes sense when you have control over the data.
Is there a cost difference between the internal storage and object storage?
Yes, obviously. In theory, it's the same, but in GCS, you can have more control on the degrees of redundancy of the data. If you don't care about the data, you can lower the redundancy and therefore pay less. But you risk of losing data, that is. Questions before we proceed? Okay. So the pros of BigQuery are, as always in any technology, there are advantages and disadvantages, and we are going to cover everything methodology. We're not too much biased because I love all the technologies we're going to discuss. There's no favorite choice of weapon. It's just a matter of use case and the right technology. So serverless, as discussed, parallelism. When you have a high degree of parallelism, BigQuery is very, very, very useful because it's serverless. So you can do whatever you like in terms of running hitting concurrency issues and avoiding, concurrency issues and not to worry about the underlying infrastructure. It kind of makes sense until 100 terabytes. when it goes over 100 terabyte to 1 petabyte, you have concurrency issues no matter what you do. I mean, you need to really drill deep into the insights of what the type of workload, who's running what type of queries, and so on and so forth. However, again, compared for the competition in terms of policy, it's quite a high advantage. You're not built for import-export, which is nice. The import and insert process are quite fast. It's a simple solution. You focus on insights and not on infrastructure. And for some people, this saves a lot of headache. It has a rich sequence syntax. It offers processing for semi-structured data quite easily, quite nice. You can use sharded tables, which is a powerful concept. You can connect perfectly to Airflow and Google Analytics with a seamless effort, which is quite nice. Any questions about the advantages?
Can you explain sharded tables, please?
Yes, sharded tables. Essentially, there are several ways to partition your data. BigQuery has offered another way to do that. So let's talk for a second about partition data. You have a table, and for example, in our use cases, you partition it by date and sensor ID. This will do some cost reduction every time you select a specific data set in your query. However, when you talk about sharding, it's a similar concept, but a bit different. Instead of putting one table and one partition for each day, permutation of day and sensor, you save one table per day and sensor. So essentially, if you, let's say you have 1,000 days sensor combinations, you have 1,000 tables instead of one big table, which is partition. The advantage here is, one, you can select all the different charts together in one query. For example, select, let me do some scratchable. That's right over here. Can you still see my screen?
Yes.
Select star from T, where it's a table prefix, and then you can do something like this. Okay? So essentially, this calls the 1,000 tables together and unions them before it filters them. This is quite useful when you have a large degree of partitions. We're talking about 10,000 and above. Does this answer your question?
So far, so good. Thank you, Omid.
You're most welcome. So let's talk about cons. So when you work with BigQuery, you must always have cost in mind when designing an ETL, which is a major shift, paradigm shift when you're working. Not most people are not accustomed to do that. An IF table is limited to give or take 4,000 partition. Other than that, you need to go sharding. It has a very basic GUI compared to the competition, and it has a limited number of clustering options. Clustering is, for each partition, you can divide that into smaller partitions. And if you are in a petascale use cases, you're more likely than usual get this error message, which is resources exceeded warning. That means essentially you run a query that runs too many resources in the background and it will not finish simply because they are unwilling to finish processing this query. And there's virtually nothing you can do except rewriting your query and dividing that into smaller chunks. Given large join query, you can easily break BigQuery in terms of processing. It doesn't work well with joins, unfortunately. It's not because BigQuery is not a good technology. It's simply because it's a scale-out architecture. So essentially for each query you're running, there will be 2,000 CPU cores going up as containers trying to process parts of the query and then sending the result to the next layer and the next layer until there's a point where one container is supposed to process the result and it fails due to memory issues. There are not too many options to do some performance fine-tuning, except rewriting your query and going over your execution plan. And it only runs on Google Cloud. Some people find it very useful to use a cloud vendor agnostic. Given our framework, there's another issue you should be aware of when considering a petascale use case. There's a problem called the knee problem. It's essentially a mathematical inflection point in your processing, where the two axes are the time it takes to complete a query and the volume of data. Essentially a big data problem, given the IBM 4Vs analysis, would assume, let's remind ourselves of the 4Vs analysis for everybody. Remember volume, velocity, veracity, and variety, this one. So essentially, the knee problem is when you have so much volume of data, it starts very nice where every change in the data is hardly felt, but there's a point where it becomes slower and slower, and then there's a point where it becomes so slow it might not even finish and sometimes even crash. This is a common issue for every technology, not a BigQuery issue. Every technology has this problem. In terms of response time, it's relatively fast. I mean, compared to hot data, it has a relatively fast response time, but it's not designed for a millisecond response time, which is understandable. But just to put things in perspective, this is what you should expect. In terms of best practices, unless you have a advanced understanding of how BigQuery works, use internal storage, it will work best for you. Use flat sharded tables or flat naive tables. Use quota protection for your cost consciousness to avoid unexpected billing issues. Avoid highly nested views. This will slow you down dramatically. You won't be aware about the underlying reason for that because it requires a lot of compute power. Use the with syntax to make your queries very, very clear. It works well in BigQuery. And you can use GCP project to divide your data set into business units and have fine-grained security. Any questions?
A question for Redshift, you can have your own cluster. So
Yes.
that way you guarantee that you have a security around your own cluster and for your data and blah, blah. But BigQuery looks like it's a multi-tenant serverless shared platform. How does BigQuery guarantee the security of my data when the platform is being shared by multi-tenants? Like,
The
or
short
kind of have
story,
my own cluster for BigQuery, like we have on the Redshift.
the short story, it's more secure than you may think.
Okay.
And the long story is that they have built it in such a way where you have resources that are only working for you. They
Oh,
go
okay.
up, they launch, they ask for the necessary permission from you. They do only the processing on your data and nothing else. They shut down, they don't exist anymore. So essentially, it's more secure than having a server working 24/7, which can be brute forced.
Okay.
But you
Got
should
it.
be safely assuming that both solutions can be very secured.
Thank you.
You're most welcome. BigQuery TCO analysis. So again, this is just a framework I'm offering. It's not something you should take for granted as if this is the cost of using BigQuery for 1 petabyte use case, because it can widely different from every use case to every use case. For example, in terms of storage, we discussed about your consideration for whether or not you are compressing or not. And I would argue that you would use the 1 petabyte on external storage and you pay, give or take, $5,000, and you load the same data to BigQuery, only this time you'll pay $24,000. And you want both. You know why? Two reasons. One, the ability to go back in time. Assuming you loaded the data and you got everything horribly wrong and you created a horrible data model, you'll be able to rebuild everything from scratch. This is one reason. The second would be, imagine a user that by mistake deleted our 1 petabyte table. Stories have happened. People have made mistakes, so you want to have some sort of a disaster recovery plan. Maybe you want to consider here a lower storage, redundancy, availability settings to decrease this cost by 2, by 4, by whatever you like, whatever you feel comfortable with. And there's another reason. If you, as discussed, put 1 petabyte on external storage, you might be able to use several types of compute on this external storage, because the storage is accessible for any technology that can use external tables. So it kind of makes sense if we ignore cost. In terms of architecture, it makes sense. Moreover, there's no licensing cost because you pay as you go. And I took the liberty to use 10 users, one full scan per month on the entire 1 petabyte. It's not reasonable, but just to get a sense of how much money are we talking about? It's about $6,000 per query. Multiplied by 10 users, it's 60,000 per month. So essentially, it gives you a very high number yearly. But obviously, this is not a real life scenario. And you can choose a flat rate for that, or examine your own assumptions for your workload and do your calculation. Perhaps there's only one full scan per month, and the rest will be on just minor data sets or the last few days, aggregated layers, or any type of calculation that will make more sense to your workload. In terms of support, we sometimes want to use support. There are some tips and tricks that working closely with support will make your life easier, especially when it comes to the complex syntax and some questions about cost and partitioning and some weirder messages which are not readable. In the end of the day, if you connect everything together, you get about $1 million price tag, give or take. And if you will check the previous lectures, more or less they'll have the same price tag for the same use case on every other technology, give or take. And again, it's not a number you should take for your boss and say, listen, Omid says this is a very good price, let's take this one. No. Just a point of reference to get started the conversation. In terms of assessment, if we are comparing these 5 technologies in my framework of the faster, cheaper, simpler, usually BigQuery is fast enough for most common use cases, very simple, and it's relatively cheap compared to other solutions. Questions about this before we go to summary? Okay, so the next session would be about a different technology, quite similar in terms of framework. It's about Databricks. Again, in terms of summary, all I want to say is that this framework is the framework I use when I evaluate a new technology. Switching to Databricks. So Databricks, given our use case of 1 petabyte tensor data and 10 analysts querying the data, considering Databricks is not a bad choice. It's even a really good one. Things to know about Databricks. In terms of architecture and binning, it's a scale-out architecture with auto-scaling, and you can apply spot instances, which could be a massive cost reduction with some pros and cons analysis. It's totally decoupled, and the cost is per second, and there's additional cost for DBUs, which is the licensing of Databricks units. It supports container storage. It's mostly Spark oriented and has a very unique and nice storage format called Data Lake. And it has a really nice feature called Photon, which is essentially a C++ acceleration to the same workload. Another useful feature is called schema evolution, that you can update your schemas. You can update your schema over time, which is kind of a major advantage compared to older technologies which don't support this. Because consider altering a table of 1 petabyte, it's like mission impossible in terms of processing and time consuming and failures and blah. It's a headache, basically. In terms of data flow, assuming AWS just to keep everything a little bit interesting and keep switching things up. So if this is your 3-node cluster of Databricks, essentially there's 2 ways. You can use a Delta Lake storage format on top of S3, or you can use your own storage format on S3. Both are acceptable and make sense, but naturally using Delta Lake will have some performance gains, cost base, some feature which will make your life easier and so forth. You can use Parquet, no problem, or any other storage format you prefer. In terms of time it takes to upload 1 petabyte to Databricks, in theory, when you are converting to Databricks, you are essentially doing an insert or upload. So assuming 1 petabyte and 10 gig NIC, you're talking about a very long process in terms of effort to complete the task. Naturally, this varies drastically by the amount of machine and the amount of network cards. It's just an example for calculations. You'll get a sense of what it means to upload 1 petabyte or insert 1 petabyte. In terms of running an aggregation query on Databricks on 1 petabyte, the more you have machines, and the more you have, and the more you use an external parallel storage like S3, you will get the benefit of parallelism, and you'll get effective aggregations in relatively short time, depending on your cluster size and network card. Does it make sense?
So you're saying that you prefer S3 over Delta Lake?
Delta Lake it's a storage format. It's like saying CSV or JSON file. Delta Lake will be saved on S3.
Okay, all right.
I was ignoring the storage format for a moment and switching to processing. Assuming any storage type, the larger the cluster, the more compute power you have, the more parallelism you get. So essentially, Nitin asked the question about the difference of internal and external. If you convert the data to Delta Lake, this is your internal data. Both are saved on S3, so it's a bit confusing, but essentially, you don't have to convert to Delta Lake. You can use your own file format and just simply do a reference to your data and move on. Hope it answers the question, Nitin.
Yeah.
So the disks on this this slide, disk 1, 2, 3, are those disks internal storage or are
No,
they
the part of
external?
S3.
Oh,
The
part of
part of
S3.
S3.
I see. Okay.
Just,
Okay. It can be Azure, block storage too, can it?
yes, Azure and Delta, the Databricks works on Azure, GCP, and AWS.
Okay.
It's vendor agnostic, cloud vendor agnostic. In terms of this aggregation, this is very powerful. When you have parallelism, it's usually correct for all the scale-out technologies, but using the C++ acceleration, it could be even faster. So it's really depend on what you're trying to achieve here. Pros. There are lots of advantages associated, but Databricks, it's truly decoupled, meaning you can access the storage layer even if it's in Delta Lake format. It has an elastic cost structure. It's very relatively fast, easy to get started, very simple syntax, very popular, very fast boot, minimal waste of billing. You have an ability to time travel, which is sometimes useful. Schema evolution, which we discussed, and the photon. Any questions about the pros?
So is this your choice for streaming solution with schema evolution? Kafka
1
to
second, please. Sorry again?
Yeah, so if you had a streaming solution, so coming off of Kafka or one of the other streaming platforms, would you definitely just go to Databricks with evolution, schema evolution?
No, I need the entire use case to answer
Uh,
that. There are
okay.
many options. For example, every cloud vendor has its own streaming solution. And it's serverless, and it's managed, and it's cost effective, and you don't have to get another license, and then. Again, there are pros and cons for every technology, especially Kafka, which is a very well-known and recommended technology.
Right, right. And also, is there any benefit to the underlying technology beyond what one would want to use for, one of the other solutions?
I need you to clarify your question.
So it's Spark underneath, right? And this is the only one that's Spark based. The rest of them are more traditional data.
Yeah, just to be clear, it's Spark-based, but it has SQL
Right.
flavor. It's not strictly Spark.
For the Spark solution over the more traditional data warehouses, depending on solution.
I don't see a reason why to switch to Spark in this specific use case. I mean, it doesn't make any special benefit.
Right. You're still coming out with the same result. Yeah. Okay. Thank
Give
you.
or take, yes. Assuming you have your processing is basic aggregation, some joins, not just highly advanced recursive functions or highly advanced logic that cannot be implemented via SQL, or an advanced analytic use case like machine learning, deep learning use case. So it's out of the scope of a standard analyst use case.
Got you. Thank you.
Again, totally coupled with the use case. Contrary to popular belief, selecting a technology for a use case is not as trivial as people may think. What? It's a database. It should work. No, it doesn't work like this. Simply because it can do a lot, it doesn't mean it can do everything effectively. And part of the concept of using data lake architecture or data mesh architecture is using one storage layer, which is unique to several compute solutions. So you can enjoy the best of all the world. Does it make sense?
Sounds like,
Yeah.
it sounds like a Databricks is more like a processing framework rather than a data warehouse platform. Because
It came
Databricks,
from, yeah, you are correct. It's a bit confusing. Personally, I think Databricks is a very nice solution, but when it comes to standard analytics, there's no real benefit here.
yeah,
It
it's not really
only
a data warehouse system like a BigQuery or Redshift or Snowflake.
yes and no, because they have a SQL data warehouse implementation, which is seamless in terms of all the Spark technology complexity. You have a simple notebook with a SQL browser, and you can write standard SQL queries with databases and tables and views like you're familiar with. So, and so in theory, it's the same. In practice, totally different experience if you're used to traditional SQL solutions.
Yeah,
Okay,
sure.
but it really depends on overall what is the organization needs, what's the use case. Not a trivial answer. Yeah, listen, as a consultant, full disclosure, my work is consulting organization or what to do is given a specific use case, which technology to use, what would be the architecture. And my answer is never the same. Every customer gets a different answer. In the end of the day, the amount of technologies I can support is finite, but the list is very long. as a consultant, as a professional. And the more complicated your use case, the more complicated maths are going to be. Does it make sense?
Yes, thank you.
You're most welcome. Please keep up with the question. It's fun.
What about the use case for the AI stuff? You had, I think, just a few minutes ago mentioned that Databricks may actually have an advantage there. And I just wanted to understand what that was, what that situation was.
Can you repeat that?
I thought that you had said that Databricks may have benefits when it comes to processing machine learning workloads, as opposed to just general data analyst workloads.
Databricks has a very nice feature called Photon, which is essentially a backend rewrite from Java to C++ technology, which in terms of the end user can accelerate ×3, ×4, ×7, ×10 even your workload.
So it's not even about Spark or Java, it's about the C++ backend that it can tie into.
Yes, but in the end of the day, you should be treating this from an analyst point of view. And what an analyst wants to do is write SQL queries and do some research on his 1 petabyte. So he wants the fastest SQL and to write as many queries as he can in parallel. So the backend is really not interesting for the analyst. All he wants is a really nice, convenient, simple GUI. He doesn't want to worry about cost, and he wants his queries to finish on time. Think about the user experience. Think about what the analyst feels like when he runs a Power Query that lasts longer than 1 minute.
Okay, I was just trying to understand the machine learning part of it, because I was curious
So ask
why
questions. So ask
why
a
Databricks
question,
was,
please. Why Databricks what?
Just where Databricks fit versus some of the other ones. It seemed like it seemed like it was going to have a hard time competing compared to some of the other ones you went over.
Yes.
But if it has a specialty in machine learning, maybe that's
Yes, it
maybe
does.
that's where they make their money.
Yes. And let me even state it over here. Very good solution when it comes to advanced analytics, AI, ML, deep. Does this comment make sense for you?
Yes. Is the time travel bullet point, is that also unique?
It's not unique. Some other technologies have it, but it's very useful.
Is that considered bitemporality? Is that what that is?
I'm not sure what is bitemporality is, but the time travel functionality allows you to get historical value of a specific cell. For example, imagine a scenario where you have a specific cell in your table that the value was updated from 7 to 8 to 9 to 10 to 11. And over time, when you see the number 17, you want to know what happened here. And you want to go to previous versions of this data set to understand what happened in a specific date in the past.
The comparison I'd be making would be to like XTDB's notion of bitemporality, where they have a date that is like when the data was stored by the system, the database date, and then the date that it's valid from a business perspective. And by having two dates on each data point, then you can look at it from an application level or from a system level And that means that data can be eventually consistent in terms of time.
I think it sounds familiar, but I really need to drill a bit deeper into that to give you a more professional answer. But based on your description, I would say, yes, it sounds like the same thing.
Is that something that is available in any of the other big data processing frameworks, or is that unique to Databricks?
Let me go over them in my head. In BigQuery, I don't think there's a time travel functionality. In Redshift, I don't think there's a time travel functionality. Going over Databricks, yes, there are. And we have SQream. I don't think they have it. And Snowflake. Snowflake has a time travel functionality.
Okay. You didn't cover Snowflake in this slide deck so far, right?
No, it's the next session, session number 4.
Okay.
I'm sorry, it's a lot of information. So
it really is.
yeah.
From
This is
from what I
please.
Yeah, I think from what I learned about Databricks, Databricks claim itself as a unified analytics platform. That the advantage of Databricks is you can do all the analytics, data processing, machine learning on its platform, Databricks platform. If you're using AWS, you have Redshift or you have Snowflake. If you want to do data processing, you're doing data processing outside of that data warehouse system. You had to use your own maybe Spark engine, or you're using a SageMaker in AWS to do machine learning. But Databricks, you can do everything on it. You can run SQL, you can run Python, you can run Scala. You just opened up the Databricks interface on the web browser, and here you go. You got everything.
Yes and no.
I don't think that there's any other platform that can do those type of unified analytic as Databricks does.
Yes and no. If you compare feature to by feature, you can do everything Databricks offers in AWS and GCP and Azure as well. But what Databricks excels, given what you said, is wrapping everything in very easy and simple.
That's it.
Graphical user interface. Disagree with
there are equivalent technology on different cloud platforms, but Databricks wrap it into its own unified platform, so it's very easy to access those technologies.
Yes. Tim, regarding your comment that there's a lot of information here, I did try to make it at least consistent throughout the technologies, and I uploaded the past lectures here on the community website. On the first page, bottom left, you can just go over.
Yeah, I've been tuning in for a few sessions now, and I really do appreciate the amount of stuff you cover. It's hard to get a handle on this type of technology. I don't have a lot of experience with big data. My experience is more programming in the small, but looking into it more now, and there's a lot.
Yeah. Well, this community has helped demystifying the challenges of entry barriers to big data, and there's lots of content to be shared here over the community. If you have any ideas what will make your life easier and simplified, just drop me an email. I'll be happy to generate the content, create an event, meet again, discuss, collaborate. I mean, the idea is fun here, and there's no commercial motivation behind it. So, just talk to me.
I guess if I had an angle, it would just be like looking at trends and what things may become more dominant in the future, just because they're taking a risk with something that isn't usually standard now. So like the bitemporality in Databricks may be an increasing selling point of using something like that over one of the other ones. I mean, obviously the packaging as a platform, as opposed to parts that you have to assemble yourself, is a value add. But for somebody like me, it's more interesting to understand the component technical capabilities, because you could always build the other thing from, you know, if you use other solutions, maybe you have to do a little bit more duct taping of things together, but maybe there's a huge cost benefit, or maybe there's some other customization that you can get out of that. So those trade-offs are more nuanced. But if you just simply don't have the capability of a particular feature that is increasingly important, that could be a huge differentiator. And then that circles back around to like what employers are going to be looking for, because they, you know, once they realize that they need a certain feature, they say, oh, we just want Databricks people. We don't want, you know, other stuff that doesn't support time travel.
Well, I agree with you. It's a very nice feature, but from 120 use cases I managed in the last 5 years, I never once used it.
Interesting.
So given a specific use case in mind, maybe it will prove more valuable, but as it stands, I rarely find the need for it, unless you made a mistake.
Yeah, and maybe that analyzing stuff after the fact, it's not as important as like online data processing, where the situation at hand may still be in flux, and being able to understand why you made a decision, you know, the way you did 2 weeks ago, when the effective date showed that that had already happened 2 weeks ago. It's like, yeah, but it wasn't entered into the system until 2 weeks late. So they made a decision without that data. And being able to query back and forth between those two different ways of looking at it. But maybe when you're querying on data that is basically old news and has settled, you don't need to differentiate on those timestamps anymore.
Yeah, there are workarounds around that. If what you are referring to is stale data, when what you mentioned is that you sometimes query data that has been updated since, and they didn't get the data when they got the query result. There are ways to tackle it. It's just simple methodology. For example, every night overwrite the last month. This way you ensure the last month is always up to date.
Yeah, I guess what you're saying is that by the time data makes it to the data lake, it's settled. And so if there are some changes that for some reason affected a really old time frame, you would just overwrite it at that point. It's a rare occurrence. And maybe you analyze that data again, maybe you don't, but you just overwrite it so that if you do analyze it again, you'll have slightly better results.
Yes. So essentially, using a basic methodology, 90% of the use cases, there's really no need for time travel. But if you have a specific use case and you find it useful, this is why I put it here, so you would be aware of that.
Well, so coming back to the AI stuff, that seems to be a really hot topic with employers right now. Everybody thinks that they're going to use AI to solve all their problems, and so they only want to hire people that do AI stuff, whether it like at any level. Like if it's DevOps people, it's like, well, they have to be able to run AI DevOps. You know, if they're coding, then it's like, you know, like you can't just be a regular programmer. You have to be able to also code to AI, like either calling out to AI to get as an API or making additional AI solutions. So I wonder if the features that Databricks has in that department will become a big deal versus some of the other solutions, or is that something that the other products can get good at if there's increasing demand for?
Generally speaking, anything is possible, but however, the amount of technologies that were developed to tackle SQL analysis is staggering. In parallel, the whole topic of AI has been booming lately, partly because of two main reasons. One is the Gen AI. Now Gen AI has made everything accelerate in terms of work productivity. So it's becoming more and more clear to even non-technology people that without AI, will become obsolete. However, when it comes to doing some advanced analytic use cases, AI, deep and ML, these technologies have existed even 30 and 40 years ago, but the thing that made it boom or accelerate is the cloud technologies, because everything became more and more accessible. Compute instances, GPU instances, frameworks within the cloud providers. Don mentioned SageMaker, and Google has its own Vertex AI platform, and Azure has its own platform, and Databricks has its own platform. It's not about not advanced enough. It's just wrapped in terms of marketing packages a bit differently. So every big vendor in the data processing has its own offering around AI. It's not relevant here, not discussed here, simply because the use case is SQL analysis. Does it make sense?
Yeah. SQL is still the main chainsaw in the box for dicing up this data.
Yes. Shall I continue?
Please.
Thank you. Okay, in terms of cons, there's penalty if you do the insert time, as we discussed, to pre-process your data into Delta Lake format, and it's not super trivial to estimate the required clusters, so you may end up over-committing on a yearly basis, overspending on a daily basis, simply because it requires so much expertise to get it right. Moreover, it's not so cheap when you discuss a 24/7 use case where the server needs to be alive 24/7, so it's not really recommended for embedded BI, which is not our use case here, but still, just to get a sense, it's designed to go up and down and not stay alive. Also, like any other technology presented here so far, it has the knee problem where the more data you push, eventually there will be a point where everything will slow down and even reach a halting point. In terms of processing power and response time, it's relatively fast compared to the competition, and you can use the photon acceleration and maybe accelerate that even further. In terms of best practices, Delta Lake, there's no reason not to use it. And you can use dedicated cluster per use case. It's okay to have 10 clusters per specific workloads. And use elastic approach, let it sleep after 10 minutes of inactivity. Questions before we go to TCO analysis? Okay. In terms of TCO analysis, I simply took the Databricks calculator and did pretty much the same calculation, but it's a bit different in terms of pricing. I used the same external storage and internal storage, but only this time both of them compressed. Notice how big the difference here. And in terms of licensing, you pay here a lot more, and simply because you have the DPUs, Databricks units, which you get a headache just to understand the pricing mechanism. You can pay very much for the wrong service used, and you can pay very little if you apply the correct selection. But essentially, I put a ratio of 1-to-1 between the amount of spend on the servers and the DBUs. Usually a 1-to-1 ratio is an acceptable standard, but it could go up or down. So naturally, this could be much more expensive or much more cheaper in terms of your end of month bill. Really depends on your use case. In terms of calculation, I took this instance type and just took 10 here. You cannot apply sports here too much because these are very expensive machines and they are high commodity. They are always grabbed, so you might end up not getting the machine you are trying to provision. So you can try to apply, sometimes you'll get it, sometimes not. Really differentiates from time to time and cloud to cloud. In terms of support, you may end up using support on a regular basis. So all in all, the price tag, again, around $1 million, as was mentioned in previous use cases. In terms of assessment, yes, fast enough, simple enough, and cheap enough, and relatively okay. But if I have to be honest, it's not going to be my first choice for this use case. In terms of summary, we're going to summary both technologies, and this is where we'll end up for today. Given the complexity of what we discussed and the amount of technologies and the use case and the fine-grained details, in the end of the day, there's one simple framework I propose, to differentiate between the different technologies. Is the technology fast enough? Is it cheap enough in terms of ROI? And is it simple to use? As mentioned before by Don and Jeff and Tim, the GUI of Databricks was very nice, but there are other GUIs which are also convenient. You can connect them to different database selections. So in the end of the day, you need to understand what's your use case and what's important to you, and then compare between the different technologies. Don't forget to do a TCO analysis. I highly recommend to get console for that. You can use me for a 5-minute discussion or even paid consult. I will be more than happy to help. Be very, very careful when it comes to this scale of 1 petabyte. Very easy to get it right, to get it wrong, and make very costly mistakes. Believe me, I did those quite a few until I changed the way I think and used outside consult. I used outside consult, and they sometimes threw away 3 months of planning and research I did on my own. And several years ago, when I was just starting in the big data world, I was designing a 0.5 petabyte use case. I designed everything, the servers, the operating system, the file system, the technology, the architecture, the workload, the monitoring, did the TCO analysis, got a console for $400 an hour. Under 1 hour, he threw me my plan and said, that's very nice, but you got it all wrong. So my recommendation to you, consult. Don't hesitate to ask questions, even if you have very good understanding of what you're doing. Always defend your architecture against a fellow or colleague, someone who knows this business inside out. In terms of summary, I usually ask some I have a pop quiz just to ask you if you know how much your infrastructure costs. In terms of time preservation, we'll skip it. At the end of the day, what we're trying to achieve here is a framework which is fast, cheap, simple, and this is the way you think when you talk about data engineering and architecture. To sum up, we have our community. I urge you to go over it, review past history, content, subscribe. Please subscribe to our YouTube channel. Now, from our website, just go to the bottom left over here, bottom middle, sorry. YouTube, do a like. It will help me spread the love and the passion I have for big data for everybody. And if you want to contact me, here's my name, LinkedIn, and all the relevant links for you. If you RSVP to this session, you'll get a link in a couple of days with the recording and the slides. I look forward to see you again next week for our fourth and final session of this series of lectures. Naturally, there will be other lectures in the future going forward. If you have any ideas, requests for specific content, I will be more than happy to contribute for my time and expertise. You just need to prepare the content, launch a meetup, gather you around, and have fun. Questions before we wrap up? Nitin asked about the TCO values. I tried to explain them. The idea is to use, let's go over it quickly. 1 petabyte, you just go to AWS calculator and calculate 1 petabyte worth of storage on S3, but I applied compression of 200 terabytes instead of 1 petabyte. Again, for the internal storage, licensing, just pick this instead in the calculator, multiply it by 10, and then you'll get the DBUs. Pricing, suppose you just took the same number across the board and didn't drill too much into it. In terms of servers, as I told you, I took the 1-to-1 ratio. I pretty much aligned the numbers that the calculation would be fair to all the technologies we're going to show in this lecture. Thank you for your time. It was a pleasure. See you next time.